Welcome to this NPTEL lecture on principles and techniques of modern radar systems. We are doing tutorial, so problems on CW and pulse radar. This is the part 2. So, this is the question today. A pulse radar with MTI filter, that means the classical pulse radar thing, operates with a stallo at so and so gigahertz and a coho of so and so megahertz. The radar tracks a target which is moving radially outbound at 150 km per hour. Find the transmit frequency, the received frequency, the IF frequency, the frequency at the input of the MTI filter. So, this is a classical thing. If you just remember the block diagram, we can do this. Let us try this. So, this is tutorial 4, problem 1. Let us see. So, first I will have to, if you want to draw this, you will need to draw the block diagram. So, coho and stallo, if you remember, this was coho FC and stallo FL. So, they are put to a locking mixer. So, this output is FC plus FL, and then that here is a power amplifier. To this power amplifier, if you remember that modulator or pulsar, that thing also comes, but that does not change the frequency. So, this is FC plus FL, then it is put to the duplexer, and from the duplexer it goes to the antenna. So, that means the transmit frequency is FC plus FL, and through this antenna it also comes here. This is the receiving part. So, first there is the RF mixer. So, this RF mixer comes here, that means this frequency is actually FC plus FL plus or minus FD depending on the Doppler of the thing. So, RF mixer. So, how RF mixer strips? So, this is FL, that means you will live with FC plus minus FD, then that is given to the IF amplifier, then from there it goes to the phase detector, and to this phase detector this coho is fed. So, that means basically phase detector, that also you know it is a mixer. So, here you are getting FD, that is put to the MTI filter. This was the block diagram. So, basically the transmit frequency. So, let us now calculate the transmit frequency. So, that is part A, transmit frequency is FT, if we call, that is FL plus FC. So, that is 5.535 gigahertz plus this 0.32 gigahertz. So, that will be 5.8 855 gigahertz. As simple as that. Then what is the received frequency? Now received frequency is, if we call it FR, that is nothing but FL plus FC plus minus FD. Now out of this it is said that the target is receding. Target receding means I will get, this will be negative, so this will go out, that means this will be minus FD. So I can say that it is FL plus FC minus FD, because target is receding. And what is FD? FD is 2 FT VR by C. So 2 into FT is just now calculated 855. Remember, this is FT, actually this is the transmit frequency. So 2 into is gigahertz. Then VR. So VR is 150 kilometer per hour. So 150 into 10 to the power 3 by hour. Hour means 3600, and then divided by C. So that will give us 1.626 kilohertz. So Doppler is 1.626 kilohertz. So we can calculate what is FR. FR will be FT minus FD. So that is 5.855 minus 0.000001626, everything in gigahertz. So it is 5.854998374 gigahertz. Okay, then part D question is, what is part question D? Question D is the frequency at the input. Now the received frequency, the IF frequency. So next we will have to do C, that is FR we got. So this we have not done. IF frequency. So IF frequency is FR minus FL. So that if you do, FR is this, FL you already know, 5.535. So that if we do, it will come to be 319.9983736 megahertz. And last is, what is the frequency at the input of, at the input of MTI filter, that is FIF minus FC. FIF is this, FC is known, so it is minus 1.626 kilohertz. So this is the Doppler shift. So it is in the negative side, there is a Doppler of this. That's all. So very conceptual problem. Let us go to the next problem. what is the highest frequency that a radar can be operated at if it is required to have a maximum unambiguous range of so and so kilometer and no blind speed for targets with velocity up to 3 Mach. Mach, I think you know, 1 Mach means the speed of sound, that is 330 meter per second. So, aircrafts etc., missiles generally they have this unit. 3 Mach means 3 into sound, velocity of sound, 8 Mach means 8 into velocity of sound, etc. Generally up to 8, 9 Machs the aircraft, fighter aircrafts or these spacecrafts they can go. So, this is the first part. The second part is show that a 5 delay line canceller is equivalent to a 6 pulse delay line canceller with weights equal to the coefficients of the binomial expansion with alternating sign. Derive the expression for the ratio V 1 by V b, where V 1 is the first blind speed of a staggered PRF with n difference PRFs and V b is the first blind speed corresponding to a constant PRF waveform equal to the average of the n staggered PRFs. What is the ratio? This is a particular value is given, and so this is a, let us see this problem first, that let us solve the first part. What is the highest frequency? So that we can have that targets with up to 3 Machs, because most of the time we know that what are the enemy targets. So, in this case let us say that 3 Mach is their maximum target. So, we can easily find out that this should be within our below our blind speed. So, by that you can do so. Where is the page? So, I can say this will be tutorial 4 problem 2. So, first part is we know again that R unambiguous related to the PRF. So, C by 2 FR, and so from that FR we can calculate. FR is C by 2 R unambiguous, and that is 3 into 10 to the power 8 by 2 into this 300 into 10 to the power 3, that has been said that. So, that turns out to be 500 hertz is the PRF. So, V b first is lambda FR by 2. So, that is actually we have to find this lambda, because that will give us the frequency. So, if we solve for lambda, lambda is 2 into V b first by FR. So, 2 into what is 2 into V b first. So, 3 into Mach. So, 330 I am assuming speed by speed of sound by 500, this is meter. So, lambda is 3.96 meter. So, you can say that F max, that will be C by lambda. So, 3 into 10 to the power 8 by 3.96 hertz. So, that is 75.76 megahertz. Okay. So, up to 75.76 megahertz you can safely operate, the targets will be detected. Okay. So, where is the So what is the next problem? Show that a 5 delay line canceller is equivalent to a 6 pulse delay line canceller with weights equal to the coefficients of the binomial expansion with alternating sign. This we have shown also in the theory, but let us show. So, in the tutorial, so we have 5 delay line. So, that means this is a T, 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 5 delay line consecutively. So, this one, then we know there will be a summer. So, from here it is directly going and a delay. So, if this is x t coming, then this is that loop, this is minus, this is plus, this again will go and one will come from here, again there is a summer. So, this one with negative, this is positive. So, this will be finally our y t. So, 5 delay line. So, we can now write so for ease of a thing we can give some names, that this one we are calling A t, then let us say this one we are calling B t, then this output we are calling C t, this one we are calling D t, rest is okay. So, I can write what is A t. A t is x t minus x t minus t, B t is A t minus A t minus t, C t is B t minus B t minus t, D t is C t minus C t minus t. So, what is y t? Is d t minus d t minus t. So, d t is nothing but C t minus C t minus t minus C t minus t minus C t minus 2 t. Then you can go on putting these values, and finally I can show if you put all those values gradually. So, you will come up with this x t minus 5 x t minus t. So, I am here, there are steps, easily you can fill up those steps. 10 x t minus 2 t minus 10 x t minus 3 t plus 5 x t minus 4 t minus x t minus 5 t. So, that shows that you require 6 pulses. One is this 0, 1, 2, 3, 4, 5, 6. So, that is why 6 pulses are required, that are shown to get this output required, and also you can find out that what is 1 minus x whole to the power 5. Its coefficients are binomial. If we do binomial expansion of 1 minus x whole to the power n, so coefficients are 1 minus 5 plus 10 minus 10 plus 5 minus 1, same here 1 minus 5 10 minus 10 plus 5 minus 1. So, we have shown whatever has been asked for. But now come to the next part of the problem, this part C. Derive the expression for the ratio V 1 by V b, where V 1 is the first blind speed of a staggered pair F with n different pair Fs. This is an important thing. So, let us do this, that part C. So, suppose we are doing F r average is F r 1 plus F r 2 plus F r n different pair Fs staggered. So, F r average will be this. So, V b will be lambda by 2 F r average. Also, what is the first blind speed due to say F r 1? I am calling that V 1. So, that is nothing but n 1 F r 1 into lambda by 2. So, I can take this ratio as V 1 by V b is n 1 F r by F r v. So, that is n 1 F r 1 by F r average is nothing but F r 1 plus F r 2 plus F r n by n. Now, we also know that the relation between all these are like this. So, one by one we can all express every F r 2, F r 3 etcetera in terms of F r 1. So, F r 2 is nothing but n 1 by n 2 F r 1, F r 3 is n 1 by n 3 F r 1, F r 1, F r n is n 1 by n n F r n. So, putting all this, we can get V 1 by V b will be n by 1 by n1 plus 1 by n2 plus 1 by nn. Okay. Now, sometimes this average, instead of average of PRF, so I will write sometimes instead of PRF average, average of PRIs is used. In that case, the formula is slightly different. So, let us do that. So, in that case, we can write T average will be T 1 plus T 2 plus T n by n. So, FR average in that case is n by T 1 plus T 2 plus T n. So, that is n by 1 by FR 1 plus 1 by FR 2 plus 1 by FR n. Now, V 1 we know lambda by 2 n 1 f r 1, V b is lambda by 2 f r average. So, V 1 by V b is n 1 f r 1 by f r average is n 1 f r 1 by n by 1 by f r 1 plus 1 by f r 2 plus 1 by f r n, etc. Okay. Now, as before, we can express all these f r 2 f r 4 from that formula as so. This earlier we used, now we require this 1 by f r 2, that will be n 2 by n 1 f r 1 . Then 1 by f r n is n n by n 1 f r 1, etc. So, putting this we can get V 1 by V b is n 1 f r 1 by n by n 1 plus n 2 plus n n by n 1 f r 1. So, that will finally give you n 1 plus n 2 plus n n by capital N. So, these two formulas are a bit different, but let us see their effect is more or less same. So, for the given values for PRF based average, let us calculate what is this ratio V 1 by V b. So, it is 4 by 1 by 30 plus 1 by 35 plus 1 by 32 plus 1 by 36. So, that is 33.076. whereas PRI based average, that will give you that V1 by VB is 30 plus 35 plus 32 plus 36 by 4. So, that will be 33.25. So, in one case 33.25, another case 33.076. So, these two formulas give slightly different values, but the order of improvement with staggered PRF is always present. You see, always you are getting almost a 30 times improvement on their thing. So, I think this problem we have seen. There was another problem. A radar measures an apparent range of 12.96 kilometer when the PRF is 4 kilohertz, but it measures an apparent range of 34.44 kilometer when the PRF is 3500 hertz. What is the true range of the target? So, this is again an interesting problem. So, I will say that problem 3. So, basically the scenario is like this: your radar is sending, so I can name them, that let us say this is 1, this is the second pulse, this is the N1 pulse, and I have the target here. So, the echo is coming. Suppose this actual echo is come here. So, let me call this as delta T1. So, after N1 pulse transmission, I have got the echo. Now, in this case, the PRF is different. So, first one is this, then so the echo is coming in the same time, but this one is delta T2 and these numbers are different, 1, 2. So, last one is here, let us say N2. So, these are all with time. So, what I can always say that in reality the echo is coming same. In the first case, let us say after N1 pulses I am getting, after transmission of N1 pulses I am getting, and this time is important. So, this is my, let us call T1 and this is my T2. So, I can always equate these two times. You think that I can always write N1 T1 because this time is same. So, N1 T1 plus delta T1 is equal to N2 T2 plus delta T2. This is my equation number 1. Now, what are given? So, given things are FR1 is 400 hertz. So, T1 I am getting, T1 is 1 by this. So, that will be 250 microsecond. Then FR2 given that is 3500 hertz. Immediately it says that T2, capital T2 is 285.7 microsecond, and delta T1 is 2 R1 by C. So, that is 2 into 12.96 into 10 to the power 3 by 3 into 10 to the power 8. So, this comes to 86.4 microsecond, and delta T2 is 2 R2 by C, that is 2 into 34.44 into 10 to the power 3 by 3 into 10 to the power 8. So, it is 229.6 microsecond. So, now you will have to trial and error solve this. So, N1 into 250 plus 86.4 is N2 into 285.7 plus 229.6. So, the equation is N1 into 250 minus N2 into 285.7 is 143.2. This is my equation 2, and I know N1 into belongs to integers. So, it is apparent from this equation that N1 is greater than N2. By trial and error, you can find that N1 is equal to 4, N2 is equal to 3 satisfies equation 2. So, delta TR for true range will be 4 into 250 plus 86.4, that is 1086.4 microsecond. So, true range is R true is C into delta TTR by 2, that is 162.96 kilometer. Please go through, this is an important problem, and I conceptually it clears many things, that how in the cases actually the radar by just the two readings, apparent readings, apparent range readings, when you are varying two PRFs, you can always find what is the true range. This is the way radar finds true ranges. Thank you.